We're now going to move into the third method of doing analysis in fluid mechanics. And in order to begin this, what we're going to do is we're going to take a look at the topic of dimensional analysis and similitude. So if you recall from earlier lectures, what we've been looking at thus far, we've looked at control volume analysis or integral analysis. We then went through the process of doing control volume analysis on a differential element, and that led to the method of doing differential analysis. And when we did, I should go back, control volume, we looked at mass, momentum, and energy. And then when we did differential analysis, we came up with a number of different equations. We had the Euler equation, which is for an inviscid flow field, and we had the Navier-Stokes equations, and that would be for a viscous flow field. And as a subset of Euler, we also looked at things such as potential flow modeling, and we just briefly talked about that. That would be another method. And usually what you're either after the velocity profiles or pressure distributions, things like that in fluid mechanics. And then from the pressure distributions, you can calculate forces and moments on objects. But that was differential analysis, and we found that it's hard to come up with solutions for these. Quite often this leads to computational fluid dynamics, CFD, or very, very basic solutions are what we're able to come up with using the differential analysis techniques. So we've looked at integral, we've looked at differential. Now what we're going to move into is experimental analysis. And experiments are just what they sound like. We do experiments with real-world objects. Obviously, we can't test very, very large objects all the time when we're doing experiments, so we do scale modeling, and that's where similitude comes in. It gives us a method of being able to scale what we're doing in an experiment versus what might actually be full-scale systems. So, and the other thing that we're going to look at is dimensional analysis. That enables us to make experiments more efficient, and I'll give you a little bit of an example in this segment where we talk about that. So we're moving into the third form, and that is experiments and experimentation. Okay, and so this is kind of a long paragraph, but this kind of sums up the purpose of looking at dimensional analysis and similitude. So what we have seen is we've gone through our analysis and we came up looking at some analytic solutions, and some do exist to things such as the Navier-Stokes equations and the Euler equations. There aren't that many, and quite often the flows are not really of industrial importance or of industrial interest. And consequently, that brings in CFD, and so a lot of people have moved to CFD, taking the Navier-Stokes equations and solving them. However, even with CFD, you always want to be able to verify the results of computational fluid dynamics using experimental data. And consequently, that brings on the motivation for conducting experiments. And prior to CFD, that was really the only way that we'd be able to get really good quantitative information. And it still happens in subjects like heat transfer. The only real way that you get correlations for heat transfer is by conducting experiments. And fluid mechanics is a big part of heat transfer experiments. So what that brings us to is the fact that experiments are not cheap. They're very expensive. It costs money to fabricate models. It costs money to conduct the experiments and have all the equipment. And it takes a lot of time. Quite often when you set up an experimental apparatus, It doesn't always work the way you think it will, and you have to tweak it. So they're very expensive. And what we're going to do, we're going to take a look at an example of looking at the flow over a sphere. And so we'll go through a bit of a thought experiment in terms of what it might cost to set this experiment up. So let's look at this as an example. So this is something pretty simple. What we have is we have a sphere, maybe diameter d, and it is in a uniform flow. So we have some uniform flow coming over it, and we'll say the free stream velocity here is v. And we're interested in the drag force on that sphere. So force is equal to what? We're interested in that. But when we look at that and we think about what parameters are important in order to conduct an experiment to understand how the drag force relates to velocity, diameter, and anything else. So we look at the drag force, and let's say that is what we're interested in. So we have drag force F. And other parameters, well, I've drawn a couple of them here, obviously velocity and the diameter of the sphere. So we have d. We have the velocity, the free stream velocity. Other parameters, well, if we did this experiment high up on top of Mount Everest versus at sea level, we would have a difference. And the reason is because of the density of the air. So that would be another one, density. And finally, if we did this experiment in honey, versus in air, the drag force would obviously be very different, and so we know the viscosity of the fluid is going to be important. So typically when you do an experiment, you should be doing this type of thing. Quite often we don't, because experiments have been done before, and so we just look at the variables. But those are some of the parameters that this experiment will be dependent upon. So if we want to understand the characteristics of the drag force on this sphere, what we can say is that the force is going to be a function of a number of different variables. We can say it's going to change with the diameter, it'll change with the velocity flowing over the sphere, with the density of the fluid flowing over it, as well as the viscosity. And those are some of the parameters, and all of these can be measured. So what does that mean? That means that if you really want to understand how the force, the drag force, varies due to these other variables, you have to vary those variables. And so let's do a thought experiment here. And let's assume that we're going to do 10 points, data points, for each test or experiment. And an example of that, let's say you do an experiment where you can fix the velocity, the density, and the viscosity, and you vary d 10 times. So you have 10 different diameter spheres, and you evaluate the drag force due to 10 different diameter spheres after you fix velocity, density, and viscosity. So if you look at this and the fact that we have these 4 parameters and then this 5th one that we're interested in measuring, what that leads to, and if we were to do 10 tests for every one of these combinations, you would end up with 10 to the 4 tests that you need to conduct. So that is quite a large number, and if you think about it, these tests aren't going to take place very, very quickly. It will take time to conduct them, and so let's budget and say maybe 1/2 hour per test. And let's say you're working an 8-hour workday. 8-hour workday, 1/2 hour per test, 10 to the 4 tests. That leads to 2.5 years of experiments investigating the drag characteristics on this sphere. this is not efficient. So what does that tell us? And this is something that experimentalists and fluid mechanicists years ago came up with. They realized that this was not efficient and they needed better ways to be able to plan their experiments. So we need a more efficient way method, and the more efficient method that we will look at is dimensional analysis. And what dimensional analysis is going to rely on is a thing called dimensional homogeneity. And what that says, and we'll be using it as we go through dimensional analysis, so what dimensional homogeneity says is that all equations in physics will have the same units on both sides. And this is a common technique for any engineering student whenever you're solving a problem. If you want to check your answer, you check the units to ensure that it is consistent on the left and right. It doesn't guarantee that you've done it right, but it means that you're moving in the right direction. So an example, let's say you have distance is equal to velocity times time. Looking at the units here, we know distance, units of length, and then on the right hand side we have length time to the -1, and that is being multiplied by time, and so then what we get is length equals length. So I mean, that's a very simple one. Oops, sorry, not time. Length is equal to length, and that's a very simple one. But what it does is it provides a mechanism by which we can check things. And so when we go into dimensional analysis, we're going to be coming up with non-dimensional numbers. And the way that we're going to get these non-dimensional numbers is through dimensional homogeneity. And the non-dimensional numbers are numbers that are very important for the experiments that we're looking at. And essentially what we're doing is we're taking a bunch of data. So instead of taking, like we showed in this example, 10 to the 4 tests and all these data points, you do fewer experiments, but you collapse your data. Onto curves that have your non-dimensional variables. So you'll then be able to come up with, we'll use pi, are going to be the variables that we use, but by collapsing, all of your data points would then fall into some relation. And that's what the experimentalist is always after. And if they can get a linear relationship like that, even better. And then they have a trend that says from this, they then know pi 1 is equal to some function of pi 2, and pi will be our non-dimensional variables. And if an experimentalist can get something like that, they're very happy. And by doing this, they don't have to do thousands of experiments. They only have to do, let's say, 50 experiments or 10 experiments even, and then all the data collapses and they get a beautiful relationship like that. Life is not always that simple and clean, but sometimes it is, and that's what we look for as experimental fluid mechanicists. So we're going to move on to dimensional analysis, and I'll show you the techniques that are used to determine these pi variables, which enable us to collapse the data and make it a lot more efficient when we do experiments.